So I'm going to talk about seafloor pressure and current measurements, which are processes in the water column that are noise for geodesy. In a pilot experiment off of Oregon, along the continental slope from about 1,300 meters down to 2,900 meters depth, the ocean bottom pressures had a standard deviation of 1.6 hectopascal after removing tides and drift and low pass filtering to 3 days. And we compared 4 methods to try to subtract most of that signal. The method that worked best used currents to estimate the geostrophic pressure, which I'll talk about in a moment. And that reduced the residual to a standard deviation of 0.4 hectopascals, where a hectopascal is a centimeter of water depth. So about a factor of 4 reduction here. So I'm going to very briefly summarize that paper. It's published in JGR Solid Earth last September. And then I'll look at a geodesy array that is funded now offshore of New Zealand. It's an energetic, more energetic western boundary region. And I just talk about how the design of that is going. Here's the Cascadia. This is the off of Oregon. We had put out 4 sites. One is a reference site offshore, and others went up the slope from up to 1,300 meters. They all measured bottom pressure and currents 50 meters above the bottom to be out of the benthic boundary layer. So and so then the bottom pressure should be in geostrophic balance with those. Well, we'll get to that. And my co-PIs in that project were Kathy Donahue and Matt Way at URI. All the pressures at those 4 sites were very, very similar. As I said, they have this 1.6 hectopascal standard deviation. The peaks, the spectral nature of it was that there's peaks at, well, there's a long period of 40 days and then 14, 9, 6, 4 sort of days. And we performed a complex empirical orthogonal function analysis on it, on these data. Let's see, where did my pointer go? There we go. And the leading mode had 92% of the variance. The second mode had 6%. And the leading mode was very uniform in amplitude and phase across the slope. The second mode had a phase reversal by 180 degrees. It basically changed sign from onshore to offshore. We said the dominant structures there are coastal trapped waves. They have scales that indicate they should be in geostrophic balance. That means that the lateral gradient of pressure, is proportional to the current speed. And we'll make use of that as follows. So I went to used an array, a 2-dimensional array of currents and pressures that we had in Drake Passage. They're out there for 4 years, and we pretend that the pressures were absent at 6 of these sites. And then we'll map the pressures geostrophically to the sites and compare with direct measurements. So this just gives a little 10-day clip of the 4 years of data, just to illustrate that the pressures vary because there's low pressure centers and high pressure centers moving through, just very much like in the atmosphere, but smaller scale, smaller spatial scale. And the conclusion is that when you compare the mapped versus measured, the geostrophic versus measured pressures, they agree very well. Here we go. So back to Cascadia. We then, the 2 of the methods that worked best were, then we just subtracted the traditional reference pressure, which is these blue lines from the reference site offshore, these blue curves, and we subtracted the geostrophic pressures, which are the red curves. So the red curves have smaller variability. Their standard deviation is this 0.4 hectopascals. we went another step and applied a synthetic slow slip event at this site and illustrated that's this ramp that goes down 2 centimeters. Oopsie, 2 centimeters during 7 days, and detected them with a match filter involved with that. And it did that at 32 places every 5 days, one at a time along this 6-month record. And basically the detection was more uniform, reliable, and for the geostrophic method, and it had no false positives, no false negatives. So then jumping ahead to the New Zealand project that is now just getting underway with co-PIs Spar Webb and Matt Way and myself, and then collaborators Laura Wallace and New Zealand and Japanese collaborators. We're thinking that this array of bottom pressures and some currents, 12 currents sites in here, will remove the drift much better because it's longer duration, and many of the sites have A0A. There's current measurements on 4 well-correlated sites across here, and they have P reference sites offshore, and there's also because of the length of the span of this alongshore, there should be some sites that don't move vertically. When we hope to see maybe 2 or 3 slow slip events during this time interval. And so we'll use those as references along comparable depths as another good method. Here's just some simulation. Okay, thank you. This is simulations that Bing He at URI analyzed from data that Laura Wallace and I think probably Spar Webb provided. At those sites, once again, all the sites had very similar pressures, and she performed the CEOF analysis on those data. Again, the first mode had almost 90% of the variance. Second mode had about 6%. You see here on the second mode, there's basically a sign change from onshore to offshore at the sites, and the third mode is less well resolved. It's like that, but it's not time. So the first mode is very spatially uniform. Second mode has very weak pressures along about the 1,600 meter depth in here, and there's a sign change across the sites, 180-degree phase shift. So what we found, current meter measures help because the mapped geostrophic pressures from the currents are unaffected by any slow slip event. And so a correlated array of current measurements produces the smallest residual pressures. The offshore pressure reference sites are essential in that setup. A0A that minimizes the reference pressure sensor drift will minimize the drift at all the reference sites inshore by carrying that in. So there's a good bang for the buck in that. And because the along slope geostrophic scales are large, then the noise gets averaged out to some extent by having multiple sites and current transects along there. But the story is not simple. The real topography is complicated. There's valleys and ridges, and they cause the pressures to deviate from the ideal coastal track wave modes. There's non-geostrophic small scale pressure and current variability that I want to talk over with the physical oceanographers in our breakout session. But I think that produces irreducible residual noise. And then in our plan is we'll use the geostrophic current methods where we get the lowest residuals, and we'll use the along site reference methods at same depth to where they give the best things. So I think that's